a theory of everything physics solution using a two-step integrated physics mathematics methodology, and I am Antonio A. Colella. There are two theory of everything methodologies. First is the prevailing Hawking single mathematics step. This has been spectacularly successful for single constituent theories such as Higgs forces and stellar black holes. However, it has provided near zero theory of everything results. The second is my new two-step methodology consisting of a conceptual physics step and the math step. This is required for multiple constituent theories such as the theory of everything. There are three goals of my conceptual physics step. First, everything was defined as 20 amplified new physics constituent theories. These consisted of superstring, particle creation, inflation, Higgs forces, spontaneous symmetry breaking, dark matter, dark energy, relative strength of forces, the superuniverse, stellar black holes, black hole entropy, the black hole information paradox, baryogenesis, and quantum gravity. Each of those constituent theories will be described in the presentation. And the definition required 15 years and 250 theory of everything iterations. The second goal of my conceptual physics step is to define all 19 key outstanding questions relating to a theory of everything, such as what are Higgs forces, what are stellar black holes, what is dark matter, what is dark energy, and how did our universe start? The third goal of my conceptual physics step is to provide correct inputs for the two-part math step to follow. The first is a beyond the standard model math solution for particles, and the second is an amplified n-body simulation for cosmology. A new astrophysics mindset is required to accept the new two-step methodology. Both methodologies are essential and complementary to each other. This is the superstring constituent theory. Superstring theory unites all known physical phenomena from the near infinitely small at the Planck cube scale to the near infinitely large at the supermassive quark star matter scale. There are three superstring theory amplifications. First, there are 129 fundamental mattering force particles in our universe, each consisting of a closed string in a Planck cube. There are 16 standard model particles. Each of those is one of 16 superpartners. Each of the first 32 has one of 32 supersymmetric Higgs particles, and each of the first 64 had one of 64 antiparticles. The 129th particle is the superforce or mother particle. All particles are equivalently represented by a dynamic point particle that's a zero brane, a closed string that's a one brane, or a Calabi-Yau surface, which is a two brane. The 6 extra dimensions of string theory are the point particle position and velocity in a Planck cube. 6 quantum fluctuations jitter or vibrate the 3-point particle positions and momentums according to the uncertainty principle. Delta y times delta momentum y is greater than or equal to the Planck constant divided by 4 pi. The second amplification is all superuniverse objects are defined by a fixed background of contiguous Planck cubes. So a proton, an atom, a molecule, an encyclopedia, a person, a star, or the entire universe can be defined by a fixed background volume of contiguous Planck cubes. The third amplification is super four-string donut. Physical singularities existed at the center of a single Planck cube at the start of the superuniverse, our precursor universe, and our universe. Our universe's donut physical singularity contained 10 to the exponent 54 kilograms of energy, which is equivalent to 10 to the 94th degrees Kelvin. A physical singularity was created in our precursor universe by the evaporation, deflation, and collapse of a maximum entropy, supermassive quark star matter, to a minimum entropy, supermassive black hole energy, or the donut-shaped singularity, or a Kerr-Newman black hole, or the start of our Big Bang white hole. This shows an electron calabi-Yau membrane in a Planck cube. One way of describing a particle is by its position and velocity, that's shown by T1, T2, T3, and T4. If you join those points together, you get a closed string. If you combine hundreds and thousands of those points, they basically trace out the calabi-Yau membrane. Now, quantum fluctuations vibrate or jitter the instantaneous point particle position. So the T1 moves to the right here, to the left, to the right, and to the left. Now, if you combine the vibrating points, you get this dashed line, and this is a closed string which is vibrating. Now, the quantum fluctuations are in 6 dimensions, delta x, delta y, delta z, and the delta momentum in x, y, and g. So if you modulate these points by those 6 dimensions, the resulting points vary or vibrate in 6 dimensions, and when you combine them, you get a closed string that vibrates in 6 dimensions. This is our universe's it from qubit concept. It stands for volume of space, and I showed 3 of them in the figure. Qubit is a quantum of information. Basically, there are 22 permanent matter-force particles in our universe. Each of them has an energy, mass, charge, and spin. For example, an electron has an energy mass of 0.51 mega electron volts, spin of a half, and a charge of -1. These diagrams are shown in 2 dimensions, whereas they should be 3-dimensional. In other words, our universe is a 3-dimensional sphere. Also, the figure is not to scale because these squares are Planck cubes. Planck cubes are near infinitely small. There are almost a googol of Planck cube volumes in the volume of a single grain of sand. There are 22 permanent matter particles in our universe, and they are described by M, H, and F. M stands for one of 11 permanent matter particles. H is a superposition of 8 types of Higgs forces, and F represents 3 forces, the graviton, the gluon, and the photon. Our universe is a sphere with a radius of 46.5 billion light years, and therefore it contains 10 to the exponent, 185 Planck cubes. If I take a portion of our universe, namely our Milky Way galaxy, that is described by a sphere with a radius of 50,000 light years, and that contains 10 to the exponent 167 Planck cubes. And if from our Milky Way galaxy I select U, or an average human, that contains 10 to the exponent 103 Planck cubes. Now, any object can be taken from our universe. For example, instead of selecting the Milky Way galaxy, I could have selected the Andromeda galaxy. And in the Andromeda galaxy, I could have selected a grain of sand from one of the planets associated with one of the stars of the Andromeda Galaxy. In summary, any object in our universe can be defined by a fixed background of contiguous Planck cubes, and each one has a qubit of information, namely the energy, mass, charge, and spin of the matter or force particle. This shows the proposed standard model supersymmetric matter and force particles. On the left are the standard model, on the right are the supersymmetric. There are 4 force particles in the standard model: the graviton, the gluon, the WZs, and the photon. And there are 12 matter particles consisting of 6 quarks and 6 leptons. Over on the right side, there are 4 supersymmetric matter particles: the gravitino, the gluino, the winozino, and the photino. And there are 12 force particles, which are the superpartners of the 6 quarks and leptons in the standard model. Now, the terminology I use is P for matter force particle, subscripts 1 to 16 for the standard model, 17 to 32 for the supersymmetric particles. So, for example, if P11 is the up quark matter particle, if you add 16 to the 11, that gives you P27, or the sub-squark force particle, which is the superpartner of the up quark. Now, one of the main reasons why I did this is because each of 16 standard model particles and 16 supersymmetric particles has a supersymmetric Higgs particle. For example, if P11 is the up quark force particle, associated with that is an H11, or the Higgs force associated with the up quark. Similarly, if P16 is the photon force particle, associated with that photon is an H16, or the Higgsino associated with that photon. This shows the particle creation function on the Big Bang timeline. First, you will notice that there are 2 scales on the x-axis: time in seconds from the Big Bang and temperature in kelvins. The reason for this is every particle's creation time is intimately related to its energy mass in either electron volts or temperature. So, for example, at 10 to the minus 12 seconds, the W minus particle was created at a temperature of 10 to the exponent 15 degrees Kelvin, or according to this formula, 80 giga-electron volts. The second item you should notice in the figure is that all of these symbols are capital letters. That means the total energy mass, for example, in all the up quarks in the universe, or all the Higgs forces associated with the up quarks in the universe. Another example is capital P sub SF. That's the energy in that donut-shaped singularity at the beginning of our universe, and that consisted of superimposed superforce particles with an energy of 10 to the exponent 54 kilograms. Immediately following time t equals 0, that donut-shaped singularity was transformed to a spherical singularity via conifold transitions. And from that point on, the shape of our universe was always a sphere. At the beginning of inflation, our universe was a spherical interface inside a Planck cube. By the end of inflation, the universe was an 8-meter sphere consisting of individual superforce particles in individual Planck cubes. And at the present time, 13.8 billion years, our universe is a sphere with a radius of 46.5 billion light years. At the Planck time, or 5.4 times 10 to the minus 44 seconds, four forces in our universe were united. At that particular time, the graviton condensed out from that spherical singularity along with its superpartner, the gravitino, and their two supersymmetric Higgs particles. At the grand unification time, or 10 to the exponent minus 36 seconds, three forces in our universe were united. At that particular time, the strong force, in the form of gluons, condensed down from that spherical singularity, along with the superpartner, the neutrinos, and their two supersymmetric Higgs particles. And at 10 to the minus 12 seconds, two forces in our universe were united. At that particular time, the electromagnetic force in the form of photon condensed out, along with its superpartner, the photino. In addition, the weak force in the form of WZs condensed out with their superpartners and their four supersymmetric Higgs particles. At a time less than 10 to the minus 35 seconds, 12 superpartner forces and their 12 Higgsinos condensed out from that physical singularity. These 24 particles were X bosons or inflaton. It was the energy from those particles which expanded the universe during the inflationary period, just as dark energy, or the sum of 8 Higgs forces, expanded the universe from the start of matter creation to the present time. During matter creation, the individual superforce particles condensed into 40 transient permanent matter and force particles. By the end of matter creation, there were just 22 permanent matter and force particles remaining. This is the inflation constituent theory. Inflation is shown by this shaded area. It goes from 5 times 10 to the minus 36 seconds to 10 to the exponent minus 33 seconds. I selected the start of inflation when the size of the universe was the size of a single Planck cube, or when the radius of the observed universe was 0.8 times 10 to the exponent minus 35 meters. When I went to calculate inflation from this point to this point, the number I came out with was 10 to the exponent 36. This chart was taken from Alan Guth's book, The Inflationary Universe, and it was amplified. If you look at his original chart, he started inflation when the size of the universe was much smaller than a Planck cube. He started it around here. When he went to calculate inflation from this point to this point, he came out with the number 10 to the exponent 53. And more will be said about this discrepancy in a subsequent chart. Higgs forces were the most important of the 20 constituent theories. First, two superforce particles were God particles because from time t equals 0 to the end of inflation, our universe consisted entirely of superforce particles. Higgs particles were associate God particles because 82% of the energy mass of our universe between 380,000 years and the present time were in the form of Higgs particles. The sum of 8 Higgs force energies associated with 8 permanent matter particles was dark energy and equal to 69% of our universe's energy. Dark matter consisted of 5 particles, the xeno and photino, 13%, and 3 permanent Higgsinos, 13%. So if you add the 8 Higgs forces, 69%, and the 3 permanent Higgsinos, 13%, you get 82%. Amplified or new physics Higgs requirements were key to the theory of everything. there were 32 associated supersymmetric Higgs particles. If a standard model supersymmetric matter particle, for example, an up quark or gravitino existed, it was always associated with a Higgs force. Similarly, a standard model supersymmetric force particle, for example, a graviton or a subsquark, was always associated with a Higgsino. Now, Fermion quantum fluctuations were exactly canceled by fluctuation of the supersymmetric forces. This happened at the grand unification time, or 10 to the exponent 16 giga-electron volts. And this was documented by Sean Carroll. Perhaps the standard model supersymmetric quantum fluctuation were exactly canceled by the supersymmetric fluctuation at an energy of 10 to the exponent 19 giga-electron volts, or the Planck time. Matter creation via spontaneous symmetry breaking was the condensation of individual superforce particles to a matter particle and their Higgs force. There were 17 matter particles and 17 Higgs forces. 8 were permanent, 9 were transient. The matter particle and the Higgs force were one and inseparable. The model I used is an undersized porcupine, which contained, for example, the electron close string with overgrown spines, or three-dimensional Higgs force around that electron. The Higgs force was a residual superforce containing the mass, charges, and spin of the matter particles, and the Higgs force was a product, not the cause of spontaneous symmetry breaking. Spontaneous symmetry breaking was very similar to the condensation of H2O from steam to water to ice at a temperature from 212 degrees to 32 degrees Fahrenheit. Similarly, the superforce condensed to a down quark and its Higgs force, an up quark and its Higgs force, and an electron and its Higgs force as the temperature decreased between 10 to the exponent 25 and 10 to the exponent 10 degrees Kelvin. There is an intimate relationship between matter creation time and the energy mass or temperature of a particle. A second example is an electron was created 100 seconds after the Big Bang at a temperature of 10 to the exponent 10 degrees Kelvin, or 0.51 mega electron volts. Ice bidirectionally evaporated to water and steam as the temperature increased from 32 to 212 degrees Fahrenheit. And similarly, spontaneous symmetry breaking was bidirectional. The down quark and the Higgs force could evaporate to the superforce, and I will say more about that when I describe stellar black holes. In beta minus decay, the down quark Higgs force evaporated to the superforce, and that's new physics, which means every matter particle has an associated Higgs force. The superforce then condensed to an up quark Higgs force and a W minus and its Higgs force. In 10 to the exponent minus 25 seconds, the W minus Higgs force evaporated back to the superforce. And the superforce then condensed to an electron, its Higgs force, and to an anti-electron neutrino and its Higgs force. Mass is given to a matter particle by its associated Higgs force. The permanent electron's Higgs force gives mass to the electron. The transient W minus Higgs force, the one that was found at the Large Hadron Collider, 125 giga-electron volt, cannot give mass to a permanent electron because it only exists for a fraction of a second. 13 matter particles consisting of 6 quarks, 6 leptons, and the WZ were provided by Higgs forces. The number of Higgs forces was unknown, and the particle masses were proportional to the Higgs force. This according to Gordon Kane in a Scientific American article. Kane's 13 standard model particles were amplified to 17 standard models and their Higgs forces. The proportionality was defined as 0.26. In other words, the energy mass of P11, an up quark, which is 2.2 mega electron volts, equals 0.26 times the energy of the Higgs force associated with the up quark, which is 8.5 mega electron volts. And that constant was defined as the portion of atomic subatomic matter plus dark matter with Higgs forces divided by dark energy on a large scale, which is 490 million light year cubed. Or C equals 5 is the percentage of atomic subatomic matter in that large scale cubed, plus 13% is the number of dark matter associated with a Higgs force, divided by 69% the dark energy in that large scale cube, and that equals 0.26. This shows the up quark baryogenesis and spontaneous symmetry breaking function, which are two of the constituent theories. First, the z-axis represents superforce energy density allocated to the up quark. The x-axis is the Higgs force associated with a single up quark. The y-axis is a single Higgs force associated with a single anti-up quark. Initially, the ball was in the peak position and came down midway between the x and y axis. What that meant was the superforce condensed in equal amounts to an up quark matter particle and its three-dimensional Higgs force, plus an anti-up quark with its three-dimensional Higgs force. A portion of the up quark Higgs force was retained as the ball returned to its peak position. On the second condensation evaporation cycle, that ball came down closer to the x than to the y axis and returned back to the peak position. After n of these condensation evaporation cycles, the ball came down along the z-x plane to the position shown here. What that meant was that the superforce energy density had condensed totally to an up quark and its three-dimensional Higgs force, and none to the anti-up quark and its three-dimensional Higgs force. When the ball was in the peak position, none of the superforce energy density had condensed. When the ball was in the position shown, all of the superforce energy density had condensed. The z-coordinate of the ball represents the superforce energy density condensed to all the Higgs forces associated with all the up quarks in the universe. The z-coordinate of the peak position minus the coordinate of the ball position represents the superforce energy density condensed to all the up quarks in the universe. It took a fraction of a second for the ball to go from its peak position to the position shown here. It took another 13.8 billion years for that ball to move vertically down to its present position, which is just over the vacuum circle for up quarks. In a 13.8 billion year descent, the x-coordinate of that ball, which is the Higgs force associated with an up quark, that remained constant. Whereas the z-coordinate of that ball, which represents the Higgs force energy density of all the Higgs forces associated with all the up quarks in the universe, that slowly decreased as the universe expanded. There are 8 permanent matter particles: the up quark, the down quark, the electron neutrino, muon neutrino, tau neutrino, the xeno, and photino. Each of those had a similar baryogenesis and spontaneous symmetry breaking function to the up quark. However, there were two differences. In each case, the intercept, peak intercept on the z-axis was different for the 8 particles, and the x-coordinate of the ball, which is the Higgs force associated with that particle, that was different for the 8 positions. Baryogenesis, matter decays, and spontaneous symmetry breaking created 22 permanent matter-enforced particles in our universe. There were 8 permanent matter particles: the up quark, the down quark, the electron, neutrino, muon neutrino, tau neutrino, the xeno, and photino. There were 8 associated Higgs forces, which was dark energy, and then there were 3 permanent Higgs xenos, and there are 3 associated forces: the graviton, the gluon, and the photon. The heaviest matter particle, assumed to be the gravitino, was created first. The lightest matter particle, the electron neutrino, created last. The approximate time sequential phases were baryogenesis of 9 transient matter particles, baryogenesis of 3 permanent Higgs xenos, decay of 9 transient matter particles to 8 permanent matter particles, and baryogenesis and spontaneous symmetry breaking of 8 permanent matter particles. The baryogenesis of 9 transient matter particles, they consisted of the top quark, the bottom quark, the charm quark, strange quark, the muon, the tau, the gravitino, the gluino, and the WZs. Each occurred at a temperature related to its energy mass, and each had an up quark Mexican hat shape similar to the up quark. However, they had a different peak intercept on the z-axis and a different Higgs force. Baryogenesis of 3 permanent Higgs xenos. There was no spontaneous symmetry breaking for the 3 permanent Higgs xenos. In other words, no Higgs forces were created. The 3 permanent Higgs forces had baryogenesis at creation times related to their energy mass, and the superforce condensed to Higgs xeno and none to its associate force particle, the graviton, gluon, or photon. In the Higgs xeno version of baryogenesis and spontaneous symmetry breaking function, initially the ball was at the peak position. It came down along the z-x plane until it intercepted this circle, which is the vacuum circle for Higgs xenos associated with the graviton, gluon, and photon. In effect, all of the superforce energy density condensed to the Higgs xeno and none to the zero energy graviton, gluon, and photon. In contrast to the inseparable matter particles and Higgs forces, the 3 permanent Higgs xenos and their associated forces became independent of each other following their associated creation. Decay of 9 transient matter particles to 8 permanent matter particles was gauge mediated. The heavy matter particles and their Higgs forces decayed to lighter matter particles, their Higgs forces, and intermediate forces. For the standard model, the intermediate force were the WZs. For supersymmetric particles, the intermediate force was the Wino. For supersymmetric particles, for example, a gravitino and its Higgs force, that decayed to a photino and its Higgs force plus the Wino and its Higgs force, or the intermediate force particle. The Wino Higgs force then decayed to standard model particles and their Higgs forces. The supersymmetric decay chain ended with Zeno's Higgs forces and Photino's Higgs forces, or the stable lightest supersymmetric particle plus the standard model matter and Higgs forces. The stable lightest supersymmetric particle, or the lightest neutrino, also included 3 permanent Higgsinos. So dark matter consisted of 5 particles: the xeno, the photino, and 3 permanent Higgsinos. Baryogenesis and spontaneous symmetry breaking of 8 permanent matter particles was previously discussed. This shows the standard model matter and force particle. There are 6 quark matter particles: the up, down, charm, strange, top, and bottom. There are 6 lepton matter particles: the electron, the muon, the tau, the electron neutrino, muon neutrino, and tau neutrino. There are 4 force particles if you combine the WZ into 1. The photon, the WZ, the gluon, and the Higgs force. This is the beyond the standard model physics solution. It contains 64 matter and force particles, 16 from the standard model, which I showed you on the previous page, plus 16 supersymmetric particles, plus 32 supersymmetric Higgs particles. 22 of the particles are permanent matter particles, and they're shown in the circular area. They are much more important than the 42 shown in the angular ring. There were 6 permanent atomic, subatomic matter particles: the up quark, the down quark, the electron neutrino, muon neutrino, and tau neutrino. They represented 5% of our universe's energy mass between 380,000 years and the present time, 13.8 billion years. Then we have the photino, xeno, and photino. These are 2 of 5 dark matter particles. They represent approximately 13%. Then we have the graviton, gluon, and photon force particles. In the center of the circular area are 11 permanent Higgs particles. There are 8 Higgs forces and 3 Higgsinos. There is a permanent Higgs force associated with the up quark, permanent Higgs force associated with the down quark, with the electron neutrino, muon neutrino, tau neutrino, the xeno, and photino. The sum of those 8 permanent Higgs force energies associated with 8 permanent matter particles is dark energy, and equal to 69% of our universe's energy mass. Then we have 3 permanent Higgsinos, and they represent 3 of 5 dark matter particles and approximately 13% of our universe's energy mass. Now, going up to the annular region, on the top right are 9 transient matter particles and their 9 Higgs forces. The top quark, the bottom quark, charm quark, strange quark, the muon, the tau, the gravitino, the gluino, and the WZs. Those 9 transient matter particles and their 9 transient Higgs forces during matter creation decayed to the 8 permanent matter particles and their 8 Higgs forces in the circular area. There are also 12 supersymmetric force particles and their 12 corresponding Higgsinos. These 24 particles were the X bosons or inflatons that expanded the universe during the inflationary period. It is my intent to make the beyond the standard model solution the counterpart to Mendeleev's periodic table of elements for atoms and elements. When Mendeleev came out with a periodic table approximately 150 years ago, he identified all the detected atoms and elements. He left spaces for the undetected atoms and elements. What I did is I define the undetected particle with a star. So there is an undetected Higgs force associated with a permanent up quark, an undetected Higgs force associated with down quark, with the electron, etc. There are 47 undetected particles, 17 detected. The detected particles are first, you have 6 permanent matter particles were detected, the up quark, the down quark, the electron, neutrino, muon neutrino, tau neutrino. There are 6 transient matter particles which have been detected. The top quark, the bottom quark, charm quark, strange quark, the muon, and tau. There is one hybrid particle that has been detected, and that is the W minus. It is a hybrid particle because it is associated with the Higgs force, which makes it a matter particle, but it has a spin of 1, which makes it a force particle. Associated with that W minus is the transient Higgs force that was detected at the Large Hadron Collider, the 125 giga-electron volt Higgs force. And then there are 3 permanent force particles, the graviton, the gluon, and the photon. This shows the dark matter, dark energy, and neutrino oscillation constituent theories. First, dark matter was the lightest supersymmetric particle, or the neutrino, or an amalgam of the xeno, the photino, and 3 permanent Higgsino. Dark matter agglomeration started 30,000 years after the Big Bang, and it formed the galaxy framework nodes. At 380,000 years, electrically neutral atoms formed, and they began to clump around those dark matter galaxy nodes. Dark energy was the sum of 8 permanent Higgs force energies. The cosmological constant was proportional to dark energy density, or the cosmological constant equals a constant in the parentheses times dark energy density. Dark energy, or vacuum density, was uniformly distributed in our universe on a large scale, and it was the sum of 8 permanent Higgs force energy densities. It decreased with time along with the cosmological constant as our universe expanded. The amount of dark energy in our universe is a constant. As our universe expanded, dark energy per unit volume decreased. And since the cosmological constant is directly proportional to dark energy density, the cosmological constant also decreased. So the cosmological constant is not a constant, but it decreases with time. Neutrinos oscillated between 3 flavors using the seesaw model and a neutral heavy lepton. The 3 neutrino flavors were electron neutrino, muon neutrino, and tau neutrino. In the seesaw model, the neutrino mass was m subscript d squared divided by m NHL, where md was the standard model direct mass and m NHL was the neutral heavy lepton mass. The neutral heavy lepton was also assumed to be the 4th family neutrino, either a xeno or a photino. There were 3 types of sequential universe expansion. The first was between time t equals 0 and the beginning of inflation. This was driven by entropy increase of the supergraviton particles. And it was similar to the loosening of a smaller than Planck cube sized sphere of vibrating strings. The second was the inflationary period which was similar to a water container freezing and bursting. At the start of inflation, our universe was a spherical singularity inside a Planck cube. By the end of inflation, our universe was an 8-meter sphere with individual Planck cubes containing individual superforce particles. The 1 to 7 Planck cube expansion caused this expansion. More energy exists in liquid than frozen water. When water freezes, latent heat is released. The X bosons, those 12 superpartner forces, the 12 Higgsinos, plus the 24 antiparticles, were the latent heat energy which expanded the universe during inflation. The third expansion was from the start of matter creation to the present time. Dark energy drove that third expansion. The product of our universe's expansion rate and the graviton's intergalactic propagation time was string theory's 7th extra dimension, and the expansion rate is a function of time. This shows the amplified messenger particles and relative strength of forces constituent theories. First, the messenger particles were amplified to contain embedded clocks and computers. Newton's gravitational force, F equals G m1 m2 divided by r squared, where m1 and m2 are two masses, for example, an up quark and a down quark. R is the range between the up quark and the down quark, and G is the gravitational constant. The graviton extracts the mass m1, the up quark, from the transmitting particle's Higgs force. A clock is initiated when the graviton is sent, and it stops when the graviton is received. The graviton computer calculates the range factor as 1 over the reception time minus the transmission time multiplied by the velocity of light squared. The graviton extracts the receiving mass, m2, for the down quark and the gravitational constant from the receiving particle's Higgs force. And then the gravitational clock computer calculates the gravitational force from this equation and provides it to the receiving down quark particle. And the gravitational force consists of a continuous series of these graviton messenger particles. The relative strength of the gravitational and electromagnetic weak force was due to a propagation factor dilution. The gravitational force was activated first and diluted by 10 to the exponent minus 39, the hierarchy problem, by the time the electromagnetic weak force was activated. All the forces were united and the strength equal at the Planck time. The heaviest matter particle was assumed to be the gravitino. The gravitino energy was created at the Planck time, but it was only activated when the gravitino condensed at the time T sub g. And that is shown on this diagram. We know the WZ force was created 10 to the exponent minus 12. And if you go up on the dashed line and over to the left, this gives the radius of the universe when the WZ force was created. Now going down by a factor of 10 to the 19th, which is equivalent to that hierarchy factor, 10 to the 38, this gives the range of our universe, the radius of our universe, when the gravitino was activated. And if you follow this dashed line over into the bottom, that time comes out to be 10 to the exponent minus 33 seconds. So, the gravitino was created at 10 to the exponent minus 33 seconds, or approximately 10 to the 25th kelvins, or 10 to the exponent 21 electron volts. The supersymmetric particles were incorrectly estimated by Snowmass because their heaviest particle was 1500 gigaelectron volts, and that is much less than what I predicted for the gravitino, 10 to the exponent 21. The amplified superuniverse. The superuniverse consists of nested parallel precursor universes, and precursor universes consisted of nested universes. Our universe is nested within our precursor universe, which is nested within the superuniverse. The superuniverse was modeled as a near infinitely large gumball machine, where our gumball, our universe, has a radius of 46.5 billion light years. The parallel universes are the other gumballs, and they have different radii. A subset of the gumballs, which contain our universe, is our precursor universe, and the entire gumball machine is the super universe. Universal laws of physics and structure were assumed across the super universe. Our universe was homogeneous and isotropic on a large scale, the 490 million light year cube. And as in our universe, the super universe had the same 129 fundamental matter and force particles. It had 8 permanent matter particles, and there were 8 associated Higgs forces, which was dark energy, and atomic, subatomic matter, dark matter, and dark energy were uniformly distributed on a large scale. Amplified stellar black holes. Stellar black hole theory was amplified to include both a quark star matter and a black hole energy because of an inconsistency in the definition of a stellar black hole. On the one hand, they said a stellar black hole had a singularity, which meant minimum area, minimum volume. And in the same breath, they said that same stellar black hole had maximum entropy, which implied maximum area or volume. So a quark star matter was defined, which had mass, volume, near zero temperature in accordance with the black hole temperature formula. It had permanent, and it had maximum entropy. In contrast, its associated black hole energy had superforce energy. It had a donut physical singularity. It had near infinite temperature, transientness, and minimum entropy. 6 types of stellar black holes were defined. Supermassive quark stars matter, and quark star matter existed in universes. There was a supermassive quark star matter between 10 to the exponent 6 and 10 to the exponent 10 solar masses at the center of each of the 100 billion galaxies in our universe. Quark stars matter range in value from several solar masses to 10 to the exponent 6 solar masses. And LIGO recently measured the merger of 2 stellar black holes, which were really quark stars matter. One had an energy mass of 36 and the second 29 solar masses. Supermassive quark stars matter and their associated supermassive black holes energy existed in precursor universes. And when the former collapsed to the latter, they formed universes. Supermassive quark stars matter and their associated supermassive black holes energy existed in the super universe. And when the former collapsed to the latter, they formed precursor universes. In our precursor universe, a maximum entropy, supermassive quark star matter instantaneously evaporated, deflated, and collapsed to a minimum entropy supermassive black hole energy, or a donut-shaped singularity, or a Kerr-Newman black hole, or the start of our Big Bang white hole. Einstein's general relativity is a subset of stellar black holes. The Friedmann, Lemaitre, Robinson, and Walker metric is the accepted solution. The solution describes two opposing forces which shape universes. The first is the gravity-matter term, and the second is the anti-gravity dark energy term. There was a third force, the radiation pressure, but that ended at 380,000 years after the Big Bang. Friedmann had three scenario solutions. In the first scenario solution, matter and dark energy were in close balance. From a physical singularity, that universe expanded at a decelerating rate until it reached an inflection point, and then it expanded at an accelerating rate. The best example of that is our universe, where its inflection point was 8 billion years after the Big Bang. This scenario solution applies to most parallel universes because it is a balanced and stable solution. The second scenario is where matter overwhelms dark matter. From a physical singularity, that universe expands at a decelerating rate until it reaches a maximum radius, and then it collapses back to a singularity. The best example of that is in our precursor universe, where a supermassive quark star matter evaporated, deflated, and collapsed to a supermassive black hole energy. This scenario applies only to a small percentage of parallel universes because of the second law of thermodynamics, which I will describe in a subsequent chart. The third scenario is where dark energy overwhelms matter. From a non-zero radius, the universe expands at an increasing acceleration rate. It's the least understood of the three scenarios. And finally, quantum gravity, general relativity boundary is the start of inflation. Because before inflation, our universe was either a donut-shaped singularity or spherical singularity inside a Planck cube. Following inflation, our universe was larger than a Planck cube, where quantum gravity is applicable. Amplified black hole entropy. The black hole entropy is currently defined as entropy equals eta times A times LP squared, where eta is a constant, A is the event horizon area, and LP is the Planck length. A proposed entropy formula uses Boltzmann's equation. Entropy equals K times the log of omega, where K is Boltzmann's constant. Omega is the total number of ways that n matter particles can be distributed in a quark star matter. The quark star matter contains n matter particles, each consisting of a closed string and a Planck cube, and a total of n Planck cubes containing both matter and force particles. N is approximately equal to 10 to the exponent 80. M is 10 to the exponent 167. Both N and M are large, and N is much, much less than M. According to Hokar, the total number of ways of distributing N matter particles with a volume of LP cube, or Planck cube volume, within a quark star matter, V equal 4 pi r cubed divided by 3, is as follows. and you will see the omega is directly proportional to the radius cube, or the volume of the quark star matter, and inversely proportional to LP cube, or the volume of a Planck cube. The amplified arrow of time. In our universe, the entropy increases irreversibly with time and provides a thermodynamic arrow of time. Einstein's theory of general relativity is time symmetric and apparently contradicts the second law of thermodynamics. In Schwarzschild's general relativity solution, he describes a black hole, a white hole, and the two universes are connected by an Einstein-Rosen bridge, also known as a wormhole or donut physical singularity. In a subset volume of our universe, the entropy decreased without negating the second law of thermodynamics for our universe. Our solar system was created 4.6 billion years ago, and entropy decreased because life was created. Life is synonymous with low entropy, high available energy, whereas death is synonymous with high entropy, low available energy. Our solar system was one of approximately 10 to the exponent 22 stars in the universe, and even though our solar system's entropy decreased, it was not negated because of the increase in entropy among the remaining 10 to the exponent 22 stars. The ratio of low entropy to high entropy stars was estimated 10 to the exponent minus 22. Similarly, in a subset volume of our precursor universe, the entropy decreased without negating the entropy increase over the entire precursor universe. A maximum entropy supermassive quark star matter evaporated, deflated, and collapsed to a minimum entropy supermassive black hole energy. The ratio of the supermassive quark star matter volume divided by the precursor universe's volume was defined as the dark energy reduction factor, and that was estimated to be greater than 10 to the exponent minus 22. Now this shows a supermassive quark star matter and its collapse to a supermassive black hole energy. This occurred in our precursor universe approximately 1 second before our Big Bang. First, the two stellar black holes are shown in 2 dimensions, whereas they should be 3-dimensional. For example, the radius of the supermassive quark star matter is estimated at 50,000 light years. Second, the figure is not to scale because these squares represent Planck cubes, and Planck cubes are near infinitely small. There are almost a googol of Planck cube volumes in the volume of a single grain of sand. There are 22 permanent matter and force particles in our universe and in all parallel universes. And they are shown by the letters M, H, and F. M stands for one of 11 permanent matter particles, the up quark, the down quark, the electron, neutrino, muon neutrino, tau neutrino, the xenon, photino. Each of those 8 permanent matter particles has a Higgs force. Then there are 3 additional matter particles, which are the Higgsino associated with the graviton, the gluon, and photon. H represents the superposition of Higgs forces from the first type of 8 matter particles, and F represents one of the 3 force particles, the graviton, the gluon, and the photon. Approximately 1 second before our Big Bang, this supermassive quark star matter swallowed one additional matter particle, and that was the straw that broke the camel's back. Because the maximum entropy, supermassive quark star matter instantaneously evaporated, deflated, and collapsed to the supermassive black hole energy, which was the donut-shaped singularity inside a Planck cube, or a Kerr-Newman black hole, or the start of our Big Bang white hole. This shows the quark star black hole to Big Bang transition, and it provides more detail over the chart I just showed you. Basically, the x-axis is Big Bang time plus time equals 0 and minus time equals 0. And the y-axis is the number of superforce particles. At time equals 0, our universe consisted of a donut-shaped singularity consisting of superimposed superforce particles. By the beginning of inflation, our universe was a spherical singularity inside a Planck cube, and by the end of inflation, our universe was a sphere with a radius of 8 meters consisting of individual Planck cubes containing individual superforce particles. At the start of matter creation, the individual superforce particles began condensing into 40 transient permanent matter-enforced particles, and by the end of matter creation, there were just 22 permanent matter-enforced particles remaining in our universe. Now, going over to the left side, before the start of matter evaporation, we had that supermassive quark star matter. It had a radius of approximately 50,000 light years, and it had a temperature of approximately 10 to the exponent minus 30 degrees Kelvin. At the start of matter evaporation, there was a single electron neutrino and its Higgs force at the center of that supermassive quark star matter, and it was subjected to the weight of everything over it, and that increased the temperature at the center of the supermassive quark star matter to 10 to the exponent 10 degrees Kelvin. And that caused the electron neutrino and its three-dimensional Higgs force to evaporate up to the superforce, which started a chain reaction, such that in approximately a billionth of a second, that supermassive quark star matter went from a radius of 50,000 light years and a temperature of 10 to the exponent minus 30 degrees Kelvin to this point where it was a hot quark-gluon plasma. It had a radius of 8 meters and it had a temperature of 10 to the exponent 25 degrees Kelvin. The second deflation phase, which was the counterpart of inflation, by the end of that phase, the supermassive black hole energy was a spherical interface inside a Planck cube. And by time t equals 0, that had been transformed to a donut-shaped singularity inside a Planck cube. Now this shows the ultimate free lunch theory versus a theory of everything solution using a two-step integrated physics, mathematics methodology. The first column has 3 laws of physics. The second column has the ultimate free lunch theory, which is the accepted solution as to how our universe was started. And the third was a theory of everything physics solution, which I'm proposing replace the ultimate free lunch theory as to how our universe began. The conservation of energy mass was violated by the ultimate free lunch theory because in that theory, before time t equals 0, there was nothing, or more precisely, there were quantum fluctuations. And hence the name, the ultimate free lunch theory. From nothing, our universe of 10 to the exponent 54 kilograms of energy was created. In contrast, the theory of everything physics solution satisfies the conservation of energy mass, because as I just described, before time t equals 0, there was a supermassive quark-star matter that evaporated to a supermassive black hole energy. In both cases, the energy of the two stellar black holes was 10 to the exponent 54 kilogram, and that was transferred over to the via the donut-shaped singularity to our universe's Big Bang white hole. The second law is Einstein's theory of general relativity. The ultimate free lunch violates that because before time t equals 0, there was nothing but quantization noise. In contrast, the theory of everything physics solution, just as Einstein predicted, there was a black hole on one side of the interface, a white hole on the other side. They were connected by a wormhole or donut-shaped singularity, also known as an Einstein-Rosen bridge. The second law of thermodynamics is satisfied by both. So I'm proposing a theory of everything physics solution. Replace the ultimate free lunch theory, because a theory of everything physics solution satisfies 3 laws of physics, whereas the ultimate free lunch satisfies only 1. This is an overview of the amplified cosmological constant problem, which is one of the constituent theories. Our universe is nested in our precursor universe, which is nested in the superuniverse. The cosmological constant problem is that the expected dark energy density was 10 to the exponent 100 times larger than observed, according to Sean Carroll. I assumed that the superuniverse's volume was 10 to the exponent 120 larger than our universe. Since spherical volumes are proportional to their radii cubed, the ratio of the superuniverse's radius to our universe's radius is 10 to the exponent 40, or the radius of the superuniverse is 10 to the 40th times the radius of our universe, or approximately 10 to the exponent 50 light years. Assuming equal expansion rates, for example, our universe's radius divided by our universe's age is the superuniverse's radius divided by the superuniverse's age. The age of the superuniverse is 10 to the exponent 50 years. The superuniverse was created by time sequential and concurrent cycles of Big Bangs to stellar black holes. 4 time sequential precursor universes was assumed between the superuniverse and our universe. The amplified Hubble's law existed for precursor universes within the superuniverse, the universes within our precursor universe, and galaxies within our universe. Both the amplified Hubble's law and the traditional Hubble's law are not constant, but are nonlinear with time or distance. And proof of the superuniverse's parallel universes is via the NASA IPEC extragalactic database. This shows 3 nested universes at time t equals 0. I show our universe as a singularity at time t equals 0, and I show a parallel universe of finite size at time t equals 0. That meant that this parallel universe was created before time t equals 0. Both our universe and the parallel universe are nested in our precursor universe, which is nested in the super universe. Now this shows the time sequential and concurrent cycles of big bangs through stellar black holes. There are 4 times shown on the figure: minus 10 to the exponent 50 years, minus 10 to the 25 years, time t equals 0, and the present time 13.8 billion years. At minus 10 to the 50 years, the superuniverse's Big Bang occurred. Over this time interval, that Big Bang evolved into the superuniverse. At this arbitrarily selected time, minus 10 to the exponent 25 years, a supermassive black hole was created, and from this time to this time, that evolved into our precursor universe. And as I've been describing all along, at time t equals 0, there was a supermassive black hole, which over this interval evolved into our universe. And here I show the parallel universe of finite size at time t equals 0. Now, the superuniverse is explicitly shown at minus 10 to the exponent 25 years. Our precursor universe is explicitly shown at time t equals 0, and our universe and a parallel universe are explicitly shown at the present time. However, you must remember that both our universe and the parallel universe are nested at the present time inside a precursor universe, which is nested in the larger super universe. There were 3 time sequential cycles of Big Bangs through stellar black holes. They are explicit on the diagram, and I will describe them as follows. At minus 10 to the 50 years, the superuniverse had a Big Bang. That was the beginning of the first cycle. By minus 10 to the exponent 25 years, a supermassive quark-star matter had been created. That was the end of the first cycle. That supermassive quark-star matter instantaneously evaporated to a supermassive black hole. That was the start of the second cycle. And at time t equals 0, a supermassive quark-star matter had been created. That's the end of the second cycle. That supermassive quark-star matter instantaneously evaporated to a supermassive black hole energy. That was the start of the third cycle. And at the present time, if you go to the center of any of the galaxies in our universe, you will find a supermassive quark-star matter, and that's the end of the third cycle. There are 2 concurrent cycles of Big Bangs through stellar black holes. They are implicit in the diagram, and I will describe them as follows. If at minus 10 to the exponent 25 years, a second supermassive black hole had been generated, that would have created a parallel precursor universe. And if at time t equals 0, a supermassive black hole had occurred, that would have generated a parallel universe in that parallel precursor universe. This is the amplified Hubble's law. Both the amplified Hubble's law and traditional Hubble's law are not constant. The traditional Hubble law measured the velocity of a galaxy relative to our Milky Way galaxy versus the distance of that galaxy to the Milky Way galaxy. Now, since our universe is homogeneous and isotropic, any reference point could have been selected instead of the Milky Way galaxy. In the amplified Hubble's law, the reference point I selected was the Big Bang location instead of the location of the Milky Way galaxy. And I plotted the velocity of a galaxy relative to that Big Bang location versus the time it took for that galaxy to get to its position. There are two justifications for the amplified Hubble's law. First, we know from Friedman's first scenario solution, we know what the acceleration versus time is for our universe. And in the amplified Hubble's law, I plot velocity versus time, which is acceleration. The second justification is when you're talking about the superuniverse or precursor universes, the Big Bang location of the superuniverse or the Big Bang location of our precursor universe is much more applicable than selecting the Milky Way galaxy as the reference point. Now, according to the first solution from Friedman's equation, our universe started from a physical singularity and it began expanding at a decelerating rate until it reached an inflection point at 8 billion years. And then the universe began to expand at an accelerating rate. I've approximated the acceleration curve as an inverted S-curve with straight line approximations to the curve. So once again, in Friedman's first scenario solution, our universe started from a physical singularity and it began expanding at a decelerating rate. Now the slope of this line is delta velocity over delta time or acceleration. Here the acceleration is the maximum and you will see the slopes decrease until you get to the 8 billion years where the acceleration is 0 and that is the inflection point. Then at that point, the universe expands at an accelerating rate and you can see that by the increased slopes in the straight line approximations. Now, if you consider the two most diverse points, which are 0 acceleration at 8 billion and a maximum acceleration at the present time, 13.8, you will see that the amplified Hubble's law is not a constant, but it's nonlinear with time. I also assumed that most parallel universes were created in a manner similar to our universe. So most parallel universes have a similar inverted S-shaped curve. Now, going back to the traditional Hubble's law, which is delta velocity versus delta distance, I approximated the expansion of the universe in terms of a power series in time, or the distance equals a constant b plus a constant c times t plus a constant d times t squared plus a constant e times t cubed. And if you differentiate that, you find a comparable power series for the velocity. Now, once again, if you take the two most diverse points at 8 billion and 13.8, if you calculate the division of the power series in V divided by D, and you do it for the two extreme points, the probability that you get a constant is near 0. So both the amplified Hubble's law and the traditional Hubble's law are not constant, but they are nonlinear with time or distance. This shows 4 nested children precursor universes at time t equals 0. First, the figure is in 2 dimensions. It should be in 3 dimensions. All of these precursor universes are 3-dimensional spheres. Also, the figure is not to scale because I assumed that the superuniverse's volume was 10 to the exponent 120 times the volume of our universe at the present time, and that is not shown on the figure. Now, the digits represent the kind of precursor universe. A single digit is a child precursor universe. 2 digits is a grandchild precursor universe. 3 digits is a great-grandchild precursor universe. And 4 digits is a great-great-grandchild precursor universe. So, the superuniverse consists of the PU1, PU2, PU3, PU4, PU5, and PU6 child precursor universes. The first child precursor universe, PU1, consists of 3 grandchildren precursor universes, PU11, PU12, and PU13. The first grandchild precursor universe, PU11, consists of 3 great-grandchildren precursor universes, PU111, PU112, and PU113. And the first great-grandchild precursor universe, PU111, consists of 3 great-great-grandchildren precursor universes, PU1111, PU1112, and PU1113. And the first great-great-grandchild precursor universe, PU1111, shows our universe as a singularity at time t equals 0, and the parallel universe of finite size at time t equals 0. Now, before we leave this diagram, there are no empty spaces in the superuniverse, and therefore these must be filled with child precursor universes, grandchildren precursor universes, etc. This is a proof of parallel universes that's by an existing multi-wavelength technique called the NASA IPEC extragalactic database. I previously said that galaxies in our universe are accelerating from our physical singularity origins, and galaxies in most parallel universes are accelerating from their singularity origins. The parallel universes are uniformly distributed between our universe, which has a boundary of 46.5 billion light years, and the superuniverse's boundary of 10 to the exponent 50 light years. And this was according to that gumball machine model that I described previously. The Milky Way and the closest galaxy are accelerating towards each other. The received blue shifts from the parallel universe may already exist in net, and they should be carefully re-examined. There should be many received galaxy blue shifts from the parallel universes. This is the amplified black hole information paradox. In 1975, Hawking correctly stated that Hawking radiation contained no information swallowed by a stellar black hole. In 2004, he incorrectly stated that Hawking radiation contained information. This is the black hole information paradox, which I feel is caused by misunderstanding of intrinsic and extrinsic information. The no-hair theorem states that a black hole energy has 3 information parameters: mass, charge, and spin. In contrast to the stellar black hole energy, our universe contains near infinite information. Any universe object, for example, encyclopedia's intrinsic information, consists of its molecular, atomic, nuclear, and fundamental intrinsic information. In contrast, a universe object, for example, an encyclopedia's extrinsic information, consists of written words. And these can be English, French, or binary coded words. Extrinsic information is the basis of Shannon's information theory. However, quark stars matter are dumb. They can neither read nor store extrinsic information. So it's the intrinsic information that should be analyzed when you describe stellar black holes. An encyclopedia's intrinsic information is lost in 4 star stages. If you take an encyclopedia and you drop it into a white dwarf star, the encyclopedia's molecular information is decomposed to atoms, and that molecular information is forever lost. If you drop an encyclopedia into a neutron star, the encyclopedia's atoms are decomposed to nuclear structure, and the atomic information is forever lost. And if you drop an encyclopedia into a supermassive quark star matter, the nuclear information is decomposed into fundamental structure information, up and down quarks, and that nuclear information is forever lost. And if you drop an encyclopedia into a supermassive black hole energy, the fundamental matter particles, the up and down quarks, are decomposed or evaporate into the superforce, and that fundamental matter intrinsic information is forever lost. So Hawking's 1975 solution is correct. Charge parity time CPT violation caused baryogenesis. There are 3 CPT violation arguments which support each other and my conclusions. The first is that the CPT theorem is invalid at the Planck scale, and that was by T.D. Lee. What I said was the Planck cube defined a quantum of matter particle, force particle in space, and that our universe originated as a donut-shaped singularity inside a Planck cube, and the quantum theory was invalid before inflation because our universe was smaller than the Planck cube quantum. The second argument was highly curved spacetimes violated CPT, for example, in the black hole energy singularity, and that was proposed by N.E. Mavromatis. He said, in the CPT theorem, the laws of physics are unchanged by combining CPT operations provided locality, unitarity, and Lorentz invariance is respected. He also said that violations in unitarity were caused by incoming matter information disappearing. What I just said in the previous chart was incoming matter information was lost in the collapse of a supermassive quark star matter to a supermassive black hole energy. The third argument was a quantum mechanics axiom stated that the transformation from one state to another respected unitarity and entropy preservation. That was from a Florian Hultke. What I said was that a maximum entropy supermassive quark star matter evaporated to a minimum entropy supermassive black hole energy, and entropy was reset to a minimum. The energy mass quanta in Planck cubes collapsed to a superforce singularity, smaller than the Planck cube quantum, and during the collapse, quantum theory was invalid. CPT, unitarity, and entropy preservation were violated in highly curved spacetime of both our precursor universes, supermassive black hole energy, and in its symmetrical Big Bang white hole energy counterpart. And this provided sufficient CPT violation to produce our universe's baryon to photon ratio of 6.1 times 10 to the exponent minus 10. This is the amplified quantum gravity In superstring theory, the Planck cube is a quantum of matter, force, and space, and its actions are described by quantum gravity. Each of 129 fundamental matter and force particles exists as a closed string in a Planck cube. Superstring theory, a theory of everything physics solution, and quantum gravity are identical because they unify all known physical phenomena from the near infinitely small Planck cube, which is governed by quantum gravity, with Einstein's general relativity of the near infinitely large supermassive quark star matter. These are quantum gravity interpretations for a double slit experiment. A single photon in a single Planck cube will go through a single slit with no interference pattern. Streams of single photons go through both slits, and they do produce an interference pattern. Single photon sources are picosecond light pulses or streams of photons, not single photons. Schrodinger's wave function. The quantum gravity classical physics border was an independent Planck cube which contained one of 22 permanent matter and force particles. Macroscopic objects, for example, a proton, are not obey classical physics, not quantum gravity. The Schrodinger wave function is not applicable to objects larger than a proton. The Schrodinger electron cloud model for hydrogen is a variation of the Bohr model. The Bohr model, the electron is in a discrete energy shell. In the Schrodinger electron cloud model, the electron is distributed about the shell location from the radius of the proton to 2 or 3 times the radius of the shell. This author's model is a variation of both the Bohr and Schrodinger model. Electron position is distributed inside the Planck cube, which is centered on an energy shell. Now, this is applicable to free electrons, whereas a Schrodinger electron cloud model is not suitable. In our early universe, there were free electrons, there were no associated protons, no energy shells. Schrodinger's electron cloud model is not applicable for free electrons. Entanglement. The energy, mass, charge, and spin of the singularity was distributed to fundamental particles, atoms, molecules, stars, and galaxies. However, there was no entanglement between fundamental particles. This shows the Schrodinger wave function for a theoretical zero mass, zero spin particle. I use the word theoretical because none of the 129 matter and force particles had both zero mass and zero spin. The Schrodinger wave function for a theoretical particle is the point 1.0 on the xp axis, where xp, yp, and zp are a rectangular coordinate system centered on a Planck cube. Now, a photon has zero mass and a spin of 1. So its wave function would be 1.0 as it rotates in azimuth about the zp axis and comes back to 1.0. That defines a perfectly circular string touching the 4 sides of a Planck cube. And that is the definition of a zero energy particle. There are no hills and valleys which modulate that perfectly circular string. A graviton has zero mass and a spin of 2. And its wave function would be 1.0 as it rotates in azimuth about the zp axis at twice the speed of a photon. Now, quantum fluctuations basically modulate the position of a particle in 6 dimensions: delta x, delta y, delta z, and the momentum in x, y, and z. So the Schrodinger wave function for a theoretical particle with quantum fluctuation is this distribution shown here. In other words, the most probable place of finding a particle is 1.0, but because of the quantum fluctuation, it can be anywhere in this volume. This shows a Schrodinger wave function for a Higgs force, 125 gigaelectron volts, 0 spin. Now, I'm not sure, the Higgs force gets the energy of 125 gigaelectron volts by hills and valleys which modulate that perfectly circular string which has 0 energy mass. Now, I am not sure of exactly how 125 gigaelectron volts affects the amplitude or frequency of these curves, so I basically assume there was plus or minus 0.1. In other words, the Schrodinger wave function for the Higgs force will vary between 1.1 and 0.9, and it will vary at the frequency of the hills and valleys which modulate that perfectly circular string. Now, the more general particle would be, for example, an electron that has an energy mass of 0.51 megaelectron volts. Once again, I am not sure how the hills and valleys on the electron string relate to amplitude, so I arbitrarily assume it was plus or minus 0.01. So the electron wave function would vary between 1.01 and 0.99, and it would vary between these two distribution functions at the frequency of the hills and valleys which modulate the basic string. Now, the electron has a spin of a half, and what that means is this distribution will rotate in azimuth around the ZP axis, and it will rotate at twice that speed in an elevation angle about the YP axis. In summary, the wave function of any of the 129 fundamental matter and force particles is a distribution inside the Planck cube. This shows 4 space-time examples with a fixed background volume of contiguous Planck cubes. The 3D space-time model is defined by the relative number of matter particles, the Higgs force particles, or superforce particles. Currently, a 3D space-time model is not available. There is a 2D rubber sheet model available with a heavy ball or sheet. And basically, that's a rubber sheet which has rectangular XY coordinates on it, and they place a heavy ball on the rubber sheet, and that deflects the rubber sheet downward. And that's an indication of space-time variation. I show 4 examples. All the M, H, and S particles are included in the variable size volume in the 4 following examples. The first is the vacuum of an intergalactic space. That's flat space-time. Basically, I will put a spherical volume of a star in intergalactic space, and I will inspect all the matter and Higgs force particles in that volume, and what I should find is that the relative number of M particles to H particles is near 0. The second example is our sun and the Milky Way galaxy. That's a low curve spacetime. The spherical volume will include the sun. Once again, I will inspect every Planck cube in that spherical volume to detect matter or Higgs force particles. And what I will find is that the relative number of M particles to H particles is relatively low. In the third example, that's a supermassive quark-star matter in a precursor universe. That's an example of high curved space-time. The matter particles were compacted into a volume smaller than the event horizon volume. In the example I showed you, I estimated the radius of that supermassive quark-star matter to be 50,000 light years. When I go to analyze all the M particles relative to the H particles in that volume, it should be relatively high. And the fourth example is a supermassive black hole energy in our precursor universe. That's a very high curved space-time because all of the energy is in superforce particles at the center of a single Planck cube. The Planck cube volume is used. The matter particles evaporated to superforce particles in a donut-shaped singularity. And variations in the supermassive black hole energy sizes can be shown by including the energy mass value. So for example, in our universe, the energy was 10 to the exponent 24 solar masses. A parallel universe could have been 10 to the 30th solar masses, and this would indicate a much higher space-time curvature than for our universe. This is the theory of everything's second mathematics step. The conceptual physics step provided correct inputs for the two-part math step. The first part is for particles, and that's an amplified standard model mathematics shown by this equation. And the plan is to prioritize and analyze 6 time periods from time t equals 0 to the present time. For example, the first period is between time t equals 0 and the beginning of inflation. During that period, our universe consisted of either a donut-shaped singularity or spherical singularity of superimposed superforce particles. The second time period is during inflation. At the beginning of that period, our universe was a spherical singularity inside a Planck cube. At the end, it was an 8-meter sphere consisting of individual Planck cubes containing individual superforce particles. The third period is during matter creation, and that by far is the most complicated period to analyze because the individual superforce particles condensed to 40 transient permanent matter force particles during matter creation, and by the end of matter creation, there were just 22 permanent matter force particles remaining. The fourth period is during nucleosynthesis. That was where the ratio of protons and neutrons in our universe went from 6 to 1 to 7 to 1. The fifth period is between 200 seconds and 380,000 years after the Big Bang. That consisted of 22 permanent matter force particles plus radiation. And the sixth period was between 380,000 to the present time, and that consisted of 22 permanent matter and force particles. So, the first, second, and fourth periods were the least important particle types. They were simple to analyze, and they were temporarily ignored. The sixth period is analyzed first. That was from 380,000 years to 13.8 billion years, and that consisted of 22 permanent matter and force particles. This was approximately 99.99% of our universe's lifetime, and the standard model mathematics solution given here must be amplified to include 22 beyond the standard model permanent matter-force particles. The fifth period is analyzed next. That consists of the sixth period, 22 permanent matter-force particles plus radiation. And then the third period is analyzed last because that's a complex time-varying plasma of 40 transient permanent matter-force particles. So the standard model mathematical solution given here must be amplified by two separate functions. First, it must include 40 beyond the standard model transient permanent matter-force particles, and second, it has to be a time-varying f of t function. The second mathematics step is for cosmology, and that's an amplified in-body numerical simulation described by Vogelsberger. The current illustrious uses a dark energy fitting technique instead of a dark energy prediction. Now that's adequate, but it's not as good as the prediction technique. So the theory of everything physics solution amplified requirements must be added in the amplified illustrious, and this will enable us to predict galaxy position and compare them with measured position instead of vice versa. This is dark energy prediction in the illustrious in-body simulation. It's a straw man rather than the final dark energy prediction solution. And the reason for this is dark energy prediction is viable, but it's extremely difficult. First, the number of Planck cubes in the test volume is near infinite. Second, the number of each type of 11 permanent matter particles and their spatial distribution are imprecisely known. The energy masses of 5 dark matter particles are unknown, and the Higgs force energies associated with the Zeno and Photino are unknown. The test volume includes 2 test galaxies, and there are 3 types of Planck cubes in the volume. First, type 1 contains 1 of 8 permanent matter particles, the up quark, the down quark, the electron, electron neutrino, muon neutrino, tau neutrino, the Zeno, and Photino. Each of those has a 3-dimensional Higgs force associated with it. Type 2 contains 1 of 3 Higgs Zenos, and they have no 3D Higgs force. And type 3 contains the superimposed Higgs forces from the type 1 particles. Now, a 3D dark matter weak lensing map and a galaxy mass map were assumed available for the 2 galaxies in the test volume. And these 2 types of maps are discussed by M. Oguri in his article. First, I will calculate the sum of all Higgs force energies in each Planck cube of type 3, and then I will calculate the following for the test volume: the average dark energy density, the cosmological constant, the average matter density, the first gravity matter turn, and the third anti-gravity dark energy turn of the general relativity equation. Then the computed acceleration in the scale factor and the scale factor A are equated to the dark energy equations, which I described before, where D, or A, equals a constant B plus a constant C times T plus a constant D times T squared, etc. And the calculations are repeated for different galaxy combinations in different test volumes to best fit the dark energy expansion equation and define the coefficient B, C, D, E, and F. Now, this is the validation of the theory of everything physics solution. There are 4 existing validations which provide a preliminary 10% validation to my article's conclusions. Ley, in his article, measured a quark nova and a transition from a neutron star to a quark star. In my article, I mentioned the transition from a neutron star to a quark star matter to a black hole energy. Morandi, in his article, said there was no quintessence in the universe. The basic assumption I made was dark energy was a constant in our universe. Edmonds, in his article, said there was a relationship between the cosmological constant and dark matter. Two of the dark matter particles, the Zeno and Photino, have Higgs forces, which means there's a relationship between dark matter and dark energy. There's also a relationship between dark matter and dark energy density, and therefore between the cosmological constant and dark matter. And Longo, in his article, said that our universe was born spinning. The assumption I made was that donut-shaped singularity had energy, mass, charge, and spin. There are 4 proposed validations. The first is the existing multi-wavelength technique, NED. That would provide 20% validation. The Milky Way is accelerating toward the closest galaxy of the closest parallel universe and vice versa. Existing blue ships from the closest galaxy should be reanalyzed. The second proposed validation is the bicep 2 Planck B-mode polarization. That would provide 20% validation. Hansen, in his article, described primordial gravity waves and inflation and B-mode polarization. Mortensen, in his article, said that there was some B-mode contamination by dust polarization. Future measurements and analyses should resolve the dust polarization contribution, and they should define inflation and one of 3 exponential inflation factors selected. Little and Lyeth, in their book, said that inflation had to be greater than 10 to the exponent 26. I said the inflation was 10 to the 36, and Guth, in his book, The Inflationary Universe, predicted 10 to the exponent 53. The third proposed validation is to peer review this theory of everything article as a benchmark, and that would provide 80% validation. Several months are required to prove that my theory of everything is correct. The fourth proposed validation is to detect the 16 supersymmetric particles and the 32 supersymmetric particles. That would provide 100% validation. This requires an updated snow mass estimate, and either the Large Hadron Collider or an advanced collider is required. This requires an estimated 5 to 50 years, depending upon whether the Large Hadron Collider is adequate or a new collider has to be built. And the conclusions are, the theory of everything solution consisted of 20 interrelated, amplified new physics constituent theories. Hawking's theory of everything single math step should be replaced by the 2-step methodology, and that requires astrophysics acceptance for my 2-step methodology. 16 standard model matter force particles have to be amplified to 64 beyond the standard model physics solution. The cosmological constant and Hubble's law are not constants. Validation of a theory of everything physics solution should be initiated. That was described on the previous chart. And the theory of everything physics solution should be augmented by the second mathematics step. That plan was described in the theory of everything second mathematics step chart. and cooperative discussions are required between physicists in the 20 amplified areas and this author. Only then will a theory of everything physics solution using the two-step integrated physics mathematics methodology or the final theory and knowledge of God's mind be resolved. Thank you.